All right. Hello, hello. Um, this video is part one of section 11.3, which is probability of multiple events occurring simultaneously or at the same time. Um, the EQ is how can I find the probability of two events occurring simultaneously? So we'll talk about that. But just begin again on the theme of an ACT type warm-up question. What is the value of x when 2x plus 3 equals 3x minus 4? And this basically just means solve. This is a fancy math person way of saying go ahead and get x quote unquote by itself. Use the algebra skills you've had for years, and let's go ahead and just solve. So sometimes easier said than done. But here I have x on both sides, so I'm going to subtract 2x from both sides. Okay, that then gives me, that's gone. I have 3 equals x minus 4. To get rid of a minus 4 or the inverse operation, I'm going to add 4 to both sides. I get 7 equals x. So then I look, and sure enough, 7 is one of my options. So easy enough. But again, even that is an example of like the wording that ACT questions and the standardized multiple choice questions will take on. In a standard deck of playing cards, what are the probabilities of drawing one card that is blank? So in the last video, we talked that a deck of playing cards is 52. There are 52 cards in a deck. What is the probability that if you draw one card, it is a heart or a club? Now, something we're going to talk about a little bit today. If you see the word or, if it's this or that, and I very, very briefly touched on it in the previous video, that means I'm going to be adding something together. So how many hearts are in the deck? If you're unsure, every hearts, spades, diamonds, clubs, there are 13 of each, and that's 13 by 4 gives me the 52. So 13 hearts, there are also 13 clubs, which means my event space, heart or club, is 26 out of 52, which is half or 0.5. What is the probability that I draw a face card? Which a face card literally has a face on it, right? So there are 3 types of face cards in the deck: Jack, Queen, or King. There are 4 of each of these, so 4 plus 4 plus 4 is 12. So in this case, what's the probability that one card is a face card? Would be 12 out of 52. We use that handy dandy trick on the not trick, but the ability that the calculator has. 12 divided by 52 as a fraction is 3 out of 13, and as a decimal is 0.23. So 12 out of 52 is 3 out of 13, or 0.23 about. So you have about a 23% chance of getting a face card if you just picked one card out of the deck. And finally, we have what's the probability that is a red numbered card? Okay, so a couple things going on here. Red means that it's either a diamond or it's a heart. So there's 2 different types of red cards. And then numbered means that it has a physical number on it. So 2, 3, 4, 5, 6, 7, 8, 9, 10. If I count these up super quickly, 1, 2, 3, 4, 5, 6, 7, 8, 9. Construction, hold please. There are 9 different values that have numbers on them, which means there are 9 diamonds and there are 9 hearts. I add those together. My event space is 18 out of the 52 cards in the deck. It's aggressive today. They're sawing. Normally it's just... Ugh. So 18 out of 52 as a reduced fraction is 9 out of 26, or as a decimal is 0.346, about. Okay, so these are all theoretical probabilities, not experimental. All right, the big topic that we have to talk about today is independent versus dependent events. So in a nutshell, 2 events are independent if they have nothing to do with one another. If the one event occurring does not affect the probability of the second event occurring. And if one event does indeed affect the other one, then those are called dependent events. An example of this is like if it's if it's 10 degrees outside, what's the probability that it snows? Okay. Well, if it's 10 degrees outside, there's a much higher probability of it snowing than if it's, say, 60 degrees outside. So, like, temperature and type of precipitation would definitely be dependent events because one occurring or the value of one affects the other one. So, let's take a look at this real quick. Flipping heads on a coin. So, if you flip a coin and get heads, does that affect the probability of you rolling a 1 on a die? Again, a die is just singular of a dice or a number cube. Clearly, if I flip heads on a coin and then I go roll a die, the outcome of the die roll is not affected by whether or not I got heads. So these two would be an example of independent events. Independent. I was like, I'm missing something. Independent. Okay. Another example. How about picking an ace from a deck of cards, followed by immediately picking another ace right away? Meaning I don't put the first ace back in the deck. And if you think about, if I draw an ace out of the deck and I don't put it back, there are now fewer aces remaining than there were before. So whether or not I draw an ace on the first card will indeed affect the probability of me drawing an ace on the second card. We'll talk a little bit more about this type of situation, but these two events would be considered dependent because the outcome of the first does indeed affect the outcome of the second one. There's a formula that goes along with this that says if two events are independent, the probability of both of them occurring is simply the product or the multiplication of their individual probabilities. So a couple things going on here. First of all, this symbol in probability, it's called the intersection, but for our purposes, you can think of that symbol, that upside down U looking thing, as the word and. So this is saying the probability of A and B occurring is equal to the probability of A times the probability of B. This statement is only true if the events are independent, meaning they don't affect one another. And so this is the first like true formula that we've had for probability. And I'm gonna show you how we can use it to test for whether or not two events are independent. But again, this equality only is true if two events are independent. So, for example, what is the probability of rolling a 6 and flipping heads on a coin? Okay. Well, the first event listed here is rolling a 6. Okay. So again, if I roll a die, what's the probability that I get a 6? So the probability of roll a 6. Roll a 6. Okay. Well, the probability of that is there's 6 sides on a die. There's only one side that has a 6 on it. So the probability of that is 1/6. I'm not even going to change it to a decimal right now because it just repeats. Our second event is flipping heads on a coin. Well, we know that the probability that you flip heads, oh boy. Sometimes I'll edit out my mistakes and then sometimes I'll just laugh at myself and go ahead and keep with it. So the probability that I flip heads is 1 out of 2 because there's 2 sides to a coin and only one side has heads. Those are their individual probabilities. Now, if the question is asking what is the probability of this and flipping heads on a coin, okay, that means I want the probability of A and B Since I know rolling a die and flipping a coin are independent events, I can go ahead and just take these individual fractions and multiply them together. You can use the calculator for this, but multiplying fractions is just go straight across the top and multiply straight across the bottom. So this ends up being 1/12. That is the probability of both rolling a 6 and then flipping heads on a coin. Okay, so that's how we can kind of use that independent event equation. So another way we can use that formula is to test for independence. Okay, so I have the probability of two events are shown. Probability of event A is 0.40. Event B has a probability of 0.25, and the probability of both happening is 0.1. Are they independent? Well, what we saw is that if they're going to be independent, that means that their shared probability has to be equal to their individual probabilities multiplied together. So if we just plug in the values that we have, right, I know that, I'm going to go back here, probability of A and B is 0.1. And is that equal to 0.40 times 0.25? I can just type that in real quick and see what I get, times 0.25. Sure enough, it's equal to 0.1. So yes, the events are independent. If I got anything other than 0.1 in the calculator, the second that this value 0.1 doesn't match that value in the calculator, then you know that they are not independent, or you can just say they are dependent events. Okay, I know it doesn't say you try, but go ahead and pause real quick and see if you could test these two events for independence. Again, I'm going to take the idea that the probability of both happening has to be the probability of A times the probability of B if they are going to be independent. So if I take 3 out of 20, is that equal 2/5 times 3/4? Again, you can use a calculator if you want. This is no big deal. But it's just multiplying straight across the top and the bottom. This ends up being 6 out of 20, which does reduce, but clearly that fraction and this fraction are not the same thing, right? 3 out of 20 is not equal 6 out of 20. So then I can go ahead and make the definitive statement that these events A and B are dependent, meaning they do not affect one, or sorry, they do affect one another. The probability of one happening does change the probability of the other one happening. So that was independent versus dependent. Okay, mutually exclusive events. This is another new piece of vocabulary that's pretty important. Just because this is a phrase you'll see quite a bit. Mutually exclusive events cannot happen simultaneously, meaning in the same event, they cannot both occur. Now, we'll look at a couple examples of mutually exclusive events. Okay, but clearly, if two events can't both occur, we can go ahead and make the statement using our new fancy math symbol that the probability of A and B occurring is 0. Just by definition, if they can't both occur, then the probability of A and B is equal 0. Okay, so mutually exclusive events, they cannot both happen. So what I'd like you to do is pause real quick, take a couple minutes, and just decide yes or no. Are the two events listed mutually exclusive? Meaning, can they both occur in the same trial of an event? Okay. To organize this, what I'm going to do is I'm going to go ahead and underline the two different events, just so I can, that is a heart, sum of 8 with 2 dice, a student in choir. Okay. So if you can differentiate between what is event 1 and what is event 2, okay, then we can, this is a little bit easier to decide, are they mutually exclusive or not. Event 1, rolling an even number, so 2, 4, 6, and it has to be a multiple of 3. So the question is, 2, 4, 6, a multiple of 3 would mean 3 or 6. Is there a possibility that both events can be true with a single die? And the answer is yes, they can both occur, because 6 could fulfill both events. Okay. Here's what's kind of goofy about the wording of this. Since it is possible for both events to happen, these two are not mutually exclusive. I'm just going to use ME to abbreviate. So if it's possible for both to happen, we say they are not mutually exclusive. Okay, how about picking a card that is a heart and that is black? Now, again, if you're not super familiar with cards, with a deck of cards, that this can be a tough question to answer, but every heart in a deck of cards is by default red. So these two things cannot occur, okay, which means these events are mutually exclusive. The next one, rolling a sum of 8 with 2 dice. So if you think, if I roll 2 dice and I get a sum of 8, they add up to 8, one of which lands on a 1. Okay. Well, if one of the dice is a 1, the other one would have to be a 7. And there's no 7 on a standard 6-sided die. So it is not possible for both of these events to occur. So I would again deem these as mutually exclusive, meaning the probability that both occur is 0. And finally, a student in choir, and that same student playing a school sport. Can both events occur if I choose a student at random at Roz? Well, obviously, there's a lot of overlap between music, the arts, and sports. Okay, so is it possible for a student to be in both choir and play a school sport? Absolutely. So these two are not mutually exclusive. Okay, a lot of vocab in this short little video. And I know the EQ is how can I find the probability of two events occurring simultaneously? We're going to kind of take that. We're going to take that EQ into the second half of 11.3, and we're just going to use this video summary to talk about our 3 new vocabulary pieces. Exclusive. So independent means one event occurring does not impact the probability of another event occurring. And again, we have this formula that goes with that. And I would make a note to yourself if you are a summary writer, that symbol just means and. Okay. Dependent is just the opposite of the independent definition, but I'll briefly put dependent is one event occurring affects the probability. Probability of another event. And finally, we had mutually exclusive. And mutually exclusive are 2 events that cannot both occur. So that'll wrap it up for this first half. Hope you enjoyed.